Hi, I'm Devshi Gulati, and the title for my talk is Searching for Triple Grid Diagrams. This is the second part of a two-part talk where I will be focusing on the details. For how this relates to Lagrangian submanifolds and contact topology, please watch part one. So let's start with a recap. What is a triple grid diagram? It's a grid diagram with n vertical, horizontal, and diagonal lines having two dots inside every row, column, and diagonal. As explained in part one, triple grid diagrams represent surfaces in CP2. They can represent Lagrangian surfaces when they are fillable. So which surfaces can be encoded by them? What about Lagrangian surfaces? If we have a grid or a knot, can we make it a part of a triple grid diagram? If not always, under what conditions? When are two triple grid diagrams equivalent? Can we define moves on these? To answer any of these questions, we need examples. The problem of searching for triple grid diagrams is hard as the diagonal conditions severely limits the number of them. For this talk, I'm going to start by talking about the naive approach one might take to try and search for triple grid diagrams and the difficulties with that. Then I will cover what are geometric triple grid diagrams, how did they come about, and how they solve the difficulties of the naive approach. After which, I will discuss the moduli space of triple grid diagrams and some ongoing work related to defining triple grid pose. If you have any questions, please reach out to me or shoot me an email. Recall that we had defined what combinatorial triple grid diagrams are and how they can be decomposed into three grid diagrams. We can encode a grid diagram via two permutations, one for X's and one for O's. If the permutations are not overlapping, we get a grid. On the slide, you can see I have labeled the rows 1, 2, 3, 4, and 5. So for X's, we have the permutation 5, 4, 3, 2, 1. And for the O's, we have 2, 1, 5, 4, 3. Triple grid diagrams can also be encoded as two permutations which satisfy triple grid conditions. This leads us to the naive approach. The naive way to get examples is to look at all possible grid diagrams and check if they satisfy the triple grid conditions or not. This gives us the following algorithm. Fix a triple grid size, iterate over all possible grids, that is, all possible permutations for X's and O's, and check if this grid is a triple grid. This is a very costly approach because the complexity is n factorial squared. When I ran this for grid sizes up to 10, I got more than 800 combinatorial examples. But on closer inspection, there was a lot of symmetry and repetition. Translation. As triple grids are on a torus, taking translations is equivalent to changing the coordinate system on the torus. Orientation. Switching X's and O is equivalent to reversing the orientation for the triple grid. Cyclic permutation. If we just permute the colors, that's equivalent to relabeling the components of the trisection. Knowing all of this, we have the modified naive approach, where we just add a step of checking if the diagram that we got was equivalent by translation, reversing orientation, or cyclic permutation to any of the previously saved ones. With this modified approach, I got very few topological surfaces, out of which even fewer were fillable. Clearly, a different approach was required from this horribly time complexity, from this one having such horrible time complexity. Geometric triple grid diagrams. Recall that triple grid diagrams came from the trivial tangles of a surface in bridge position and the trisection of CP2. Also, a surface in bridge position is determined by its spine, that is, its intersection with the spine of the ambient trisection. Shadow diagrams are actually embeddings of cubic Tate-colored abstract graphs. What does that mean? Well, a cubic graph is a graph such that each vertex has 3 edges. And it's said to be Tate-colored if we can assign a color, red, blue, or green, to each edge of the graph so that every vertex has exactly 3 distinctly colored edges. We need a more flexible definition which encodes the main information, which is the cubic Tate-colored graph. So we need to allow for different spacing between the vertices. Otherwise, the diagonal condition really is very limiting. So we have the geometric triple grid diagram, which consists of 2V points on a torus, which satisfy the conditions that every horizontal line has exactly 2 points or none. So does every vertical line and every diagonal line. Now, we can think of geometric triple grid diagrams as embeddings of cubic Tate-colored graphs into the torus with additional restriction. The first restriction simply ensures that there's no overlap of vertices. The second one is the same as saying two vertices are on the same horizontal line if and only if they're connected by a red edge. And two vertices are on a vertical line if and only if they're connected by a blue edge. Same for the diagonal. This gives us a geometric triple grid diagram. With this knowledge, we have a new approach. We start by fixing a cubic Tate-colored graph gamma, and we find the embeddings of this graph, which is a polynomial in V, much, much more efficient than the n factorial squared approach. I would like to add here that I've been writing code for all of the approaches discussed, including this one. And for this particular one, finding the embeddings required some non-trivial mathematics. So the space of all of these embeddings is called M of gamma. Another advantage of this approach is orientability. A triple grid diagram encodes an orientable surface if and only if its graph type is bipartite. The naive approach assumed that the surface was orientable since we were encoding 2B points as 2 permutations, one for x's and one for o's, therefore partitioning the points. With this new approach, we can search for both orientable and non-orientable surfaces. Here is an example of a geometric triple grid diagram for RP2 showcasing this. Moduli space. With this new approach, one has to know if we will get any geometric triple grids at all. It turns out that if we take any gamma, the moduli space is a smooth manifold and is non-empty if our bridge number is greater than or equal to 3. This comes from the fact that we're essentially solving linear equations, and the degree of freedom is much more than the restrictions. In particular, if we have b equals to 1, then the moduli space is empty. If b is 2, then it consists of only one element, which is the RB2 graph shown earlier. As you can see here on the left, for b is equal to 2, we have the cubic Tate-colored graph. This is the only one that's possible. And it has only one geometric triple grid up to translation, which is in the center of the screen. For b is equal to 3, let's consider the K33 graph, which is with this Tate coloring, which is pretty symmetric. In the center, we have the geometric triple grid diagram of this graph type. On the right, we have the moduli space corresponding to this graph. This is a subset of the torus, T2. It consists of the yellow region and a blue region with this wall in the center. Each part of the square, the yellow and the blue, have two different types of geometric triple grid diagrams. And what I mean by two different types is that two different combinatorial triple grid diagrams come out of it. Let me explain that further with the next example. Let's consider B is equal to 4 and the graph gamma on the right. This encodes a torus. The moduli space for the embeddings of this lies in D3. Here is the picture. This moduli space in D3 is cut up by 6 planes, 3 of which cut it into a cube, which is shown on the screen. Further, we have 3 more walls. For the first one, let's look at the yellow and green at the back. This is showcasing how this grayed wall is cutting this cube into 2 regions. Similarly, if we look on the left, we have purple and red showcasing how this plane is cutting this cube into 2 regions. And similarly, this one is showing how the teal and orange is showing how this plane is cutting this cube into 2 regions, therefore giving us a total of 6 regions, all sharing this pink line. Each region is a space of geometric triple grid diagrams, which encode the same combinatorial triple grid diagram. On the right here is one of the geometric triple grid diagrams from one of the regions. Here are all 6 geometric triple grid diagrams for the 6 regions. And here are the 6 combinatorial triple grid diagrams we get. This is an exhaustive list of the combinatorial triple grid diagrams we get from this particular graph. In this manner, given any cubic shade-colored graph, we can get all the combinatorial triple grids corresponding to it. Ongoing work. Triple grid moves. If we go from one region to another, passing through any of these planes or walls, that is an example of a triple grid move. Let's look at these 2 geometric triple grid graphs to understand what's happening. If you see the yellow rectangles zoomed in on the right, we can see that these 2 points are being swapped. It turns out when they're crossing this wall, at that point, these points have come, in the wall, these points have come together and degenerated into something which is not precisely a triple grid. Moving through walls is like performing triple grid moves. Thank you.